In this video, I'm going to show you the full solution of 2021 Time Zone 0 Exam Paper 2 of higher level. No bullshits, let's go. In question 1, you are given with a diagram and a graph. You know the mass of the ball and you know it's dropped by height h from the horizontal floor. Note that the value of gravitational acceleration is not 9.81. It is 9.80 in this question. Moreover, we take negative 9.80 because the hidden message is we take upward as positive and downward as negative. Alright, our task in part A is to determine the value of h, which is the drop height. This is falling through the uniform accelerated motion, which means we can take Sulfat's equation. Let's begin with Sulfat's table. We take downward as negative with SUVAT on our table. The vertical drop should be negative h because downward drop by h. U was 0 because it was released from rest. The landing velocity, we don't care, just leave it blank. The acceleration, according to the question, is negative 9.80, and the time is 1.0 second. We don't know any information of v. We have nothing else but using s equals to ut plus half at squared. And substitute everything from the Sulfat table, you can get h being 4.90 meter, and it's a positive number. In part B1, we are trying to identify the maximum rebound height, and let's draw the trajectory of the ball. It's going down, bouncing up, and falling down again. Here, let's label these with different color. Firstly is the falling section. The falling sections is over here. Next one is bouncing up motion. It will be stationary at the top. So this part is the green as well as here is the green. Which means the impact moment here is this part. And lastly, the falling down section, which is here, it will be the negative velocity. With this information in our mind, where is the maximum rebound height? It should be between green and pink, which should be at time equals to 1.6 seconds. We label this point as M. Part B2, stating the acceleration of the ball at the maximum rebound height. At the maximum rebound height, what forces is acting on the ball? There's only one force, the weight. And because the weight is the only force, is the net force, which means the acceleration of the object is the gravitational acceleration. And in this question, it is negative 9.80 meter second negative 2. In part 3, we are trying to draw the height against time graph, but this graph is only showing the instant as it rebounds from the floor until it reaches the maximum bounce height, which means is my colorful drawing only the green section. Then it goes like this one. Make sure it starts from origin and it ends at 0 gradient because it's the maximum bounce height. In part C, you are going to calculate the laws in mechanical energy. Mechanical energy, which means is the sum of kinetic energy and gravitational potential energy. And the ball is hitting the ground with a large speed and bouncing back with another lower speed. Let's take the approaching speed as u and the rebound speed as v, just like Sulfat's equation. And what are u and v respectively? On the graph, you are provided with the speed between yellow and blue moments, that is the u. And reading the graph, it gives you u being negative 9.8 meters per second. And v is the speed between the blue and the green section. Therefore, it's here. It's positive 5. Then the loss in mechanical energy would be the initial kinetic energy minus the final kinetic energy. And they are half mu square minus half mv square. Then you can substitute all the numbers provided by the question, especially mass being 0.250 kilogram. Don't forget this number. U is negative 9.8 square. And V is 5 meters per second square. Then you can get the final answer, the loss in mechanical energy being 8.9 joules. In question part D1, you are trying to calculate the average impact force exerted on the floor by the ball. And let's take a look at the interaction between the ball and the floor. Here, there is a force going between these two bodies, and which is the normal reaction on ball as well as the normal reaction on floor. Our final answer is this one, normal reaction on the floor. But getting those information off the floor is not that easy. Instead, let's try using Newton's third law. Newton's third law. It suggests that the normal reaction on the ball and the normal reaction on the floor, they have the same magnitude, which means their absolute value, they are the same. Then we can focus on the information of the ball itself. Apart from there is a force acting upward by the floor, there is a weight acting downward as well. And these two forces together will give you a net force acting up. The net force on the ball is the normal reaction on the ball minus the weight. Why the net force is acting upward? Simply because the ball is bouncing up. That's why the net force is going up. And we can make use of the Newton's second law now. The Newton's second law is the net force being the rate of change of momentum. Therefore, we can put the net force on the ball is the change in momentum of the ball divided by the time taken. So, the change in momentum, according to the questions provided information, should be 0.250 kilogram times the final velocity, which is positive 5, minus 0.250 kilogram multiply negative 9.8. Divided by the time. The time is the impact time. Impact time is the width of this blue section, which is only 1 unit on the graph. 1 unit on the graph is equal to 0.1 second. So the impact time is 0.1 second. Which means the net force acting on the ball should be 37 Newton, and it is a positive value because acting on the ball is going upward. Having this net force on the ball, we can calculate the normal reaction on the ball using the previous developed relationship. Normal reaction is the net force plus the weight, which is negative 37 Newton plus 0.25 times g in negative. So the normal reaction is 39.45 Newton. And by Newton's third law, the normal reaction on floor should be in negative because of opposite direction. So the very final answer is negative 39.45 Newton. Question part 2. Conservation of momentum is under a condition, which is there must be no external resultant force acting on the system. And now, is there any external resultant force acting on the ball? Definitely yes. According to our calculation, there was an external net force acting on the ball, which makes the system no longer conserve in momentum. So the short answer here is there is an external resultant force acted on the ball. In question 2, we have a longitudinal wave and the speed of it is 340. Next, we are given with a graph. It is the displacement in micrometer against time in millisecond. Then, the positive displacement is indicating a displacement going to the right-hand side, which means the negative displacement is the left-hand side. Part A calculates the wavelength of the wave. First, for this graph, the time period is shown by comparing these 2 points. Therefore, the time period in this case should be 4 milliseconds. After knowing the time period and you're given with the speed, calculating the wavelength is not challenging. We can begin with V equals to F lambda. Meanwhile, frequency f is 1 over time period. So, lambda wavelength is the product of speed and time period. Is 340 times the time period, 4 milliseconds. The wavelength is 1.36 meter. In part B, we are going to calculate a specific particle. Particle P, its magnitude and direction of its acceleration at a specific time, t equals to 2.0 millisecond. So we focus at this point. This is the instance we are looking at. Time equals to 2.0 millisecond. And this point is displacement is -6 micrometer. So how do we relate displacement and acceleration? We can check your formula sheets. It's A equal to negative omega square x. Omega is the angular velocity of the object, and its angular velocity is 2 pi over time period. Next, we put all the information we had above into the equation, and we should get 2 pi over 4 millisecond square times its displacement at that point. -6 times 10 to the power of -6. Just put these number into your calculator and you'll get the answer, which is 15 meter per second square. Next, in part C, we're going to compare their phase relationship. Firstly, what's mean a phase? Phase is a tool helping you to compare the progress of a wave. For every one cycle, there is 360 degrees of a phase, and also it is 2 pi radian of a phase. Now we can see that on the graph, it's not able to show you a complete cycle. Instead, it's showing you 3/4 of a cycle, which means at this point is phase gonna be 270 degrees. Also, you can state this point as 1.5 pi radian. And then let's take more points into our consideration. Let's say this point and this point. Points on the left, it is a quarter of a cycle. So it is 90 degrees as well as 0.5 pi radian. The one next to it, it is 180 degrees, and also this point is 1 pi radian. To compare these two waves' phase difference, we should check a point at which they have the identical pattern. Therefore, it is these 2 points. And they are both going to the bottom right. They are differ by 180 degrees minus 90 degrees, therefore 90 degrees is your final answer. Also, you can give your answer as 1 pi radian minus 0.5 pi radian, giving you 0.5 pi radian being your answer. Next, part 2. We should locate a point at which the point P, its displacement is 0. Why the displacement of P could be 0? Because the graph is showing you two lines, and these two lines, they are the displacement of each wave acting at the position P. Which means these two lines, the solar line and the dotted line, they are interfering. They are superposing. And their interference could give you a destructive interference, giving you a resultant displacement being 0. And that is the dotted arrow going up by positive 4 micrometer and solid arrow going down by negative 4 micrometer. Therefore, these two waves, their displacement are balanced. They are cancelled out, giving you 0 displacement, being the resultant displacement at time equals to 1.5 millisecond. Part 3, estimate the amplitude of the resultant wave, which means we are looking at the maximum displacement of the whole wave, not at any instant, the maximum possible displacement. And that is happening when they are giving you a perfect constructive interference. What is the greatest constructive interference we can get? Probably it's over here. At time equals to 0.5 millisecond, these two waves, they are both acting in the positive direction by positive 4. Which means is plus 4 and plus 4 together, you have plus 8 micrometer. And that is the greatest displacement you can get, also known as the amplitude. It is 8 micrometer. In part C, there is a standing wave inside a tube, and this tube gives you an open end as well as a closed end. It's given that the wavelength of the wave is 1.20 meter. So the wave of this length should be 1.20 meter. And right now on the diagram, it's starting from equilibrium, going up, down, and end at the trough, which means is the green section over here. Then in ratio, it should be 3/4 of a wavelength, which means is 3/4 of 1.20 meter. So the answer of part D1 is 3/4 of 1.20, 0.90 meter. In part 2, we are going to state and explain the direction of velocity of a particle at the opening. It was at time equals to 0, and now it is time equals to t over 8. So the motion of this particle should be going up on our diagram. Getting upward, which means it's getting less negative. Getting less negative, according to the idea above, positive, which means going to the right. Therefore, this particle's velocity is pointing to the right. Lastly, part 3, we're going to make a drawing on the given diagram. And drawing is the instant of the wave at time equals to t over 4. Note that the given one, it was time equals to 0. And then there was a time equals to t over 8. Lastly, we're going to draw time equals to t over 4. From the first given one to the second given one, 1/8 of a time period has passed. And also from the t over 8 to t over 4, there is also 1/8 of time period passed. Which means we should just continue the motion that it was given. They were heading down on the left-hand side, so it's still heading downward on the left-hand side. Therefore, it's still heading upward on the right-hand side. So the final answer of the drawing should be a complete flat line going along the equilibrium. In question 3, you're given with two positive charges and they are both positive 44 microcoulomb. These two charges together with point P creating an equilateral triangle. The side of this equilateral triangle is 0.48 meter. Lastly, we're going to calculate the magnitude of the electric field strength at P is going to be roughly this value. Once again, it's a show that question, and our target is one significant figure, which means our final answer should be at least 2 sig fig or even more. What is the resultant electric field strength at P? It is the result of the electric field strength due to the left-hand side one and the right-hand side one. Then together it will give you the net field strength or the resultant field strength. The field strength from the left-hand side is stretching out because it is a positive charge, so it is creating an outward field. Let's take this one as a green charge. It's creating an outward field. And this outward field would expand until it reaches point P. It is going to top right-hand corner. The field strength at this point can be calculated using the equation of E equals to F over Q. And because it is a radial field, we can take KQQ over R squared for the force divided by the small q. Simplify it to be K big Q over R squared. So the field strength is K, which is the Coulomb constant in your formula sheets. Charge of big Q, which is 44 times 10 to the power of negative 6. Distance 0.48 square. It is 1.72 times 10 to the power of 6. But this is going top right hand corner, not vertically up nor horizontally to the right. Why do we study its components? Because don't forget there is another particle, the plus Q on the right. It's also creating an electric field strength going to the top left hand corner and is partially cancelled in the horizontal direction. In other words, our final electric field strength should be 2 times of their vertical components. So the net field strength will be 2 times of the field strength in vertical. How do we get the vertical field strength? We should study the angle. The angle over here. The angle over here is the same as angle over here. As this is an equilateral triangle and angle theta is half of one of its angle, therefore angle theta should be 60 degree divided by 2. It's 30 degree. The answer is 2 times of their vertical components, which is 1.72 times 10 to the power of 6, and then cos 30 degree. And the answer is 2.97 times 10 to the power of 6 Newton Coulomb negative 1. The direction of resultant electric field at P would be vertically going up. Because those horizontal components, they are balanced, the answer is simply vertically going up. In part B, things are getting more complicated. Firstly, we still have the positive charge just like the old time, and now at point P there is a negative charge, which means this point P negative charge is being attracted to both positive charge, and the resultant force acting on it should be going to be vertically downward, pointing towards the intersection. And as it gets further away, the force will be stronger because of the net force is resolved from the components of the two attracting force. After all, the particle is oscillating on this yellow line, and its oscillation shall be a simple harmonic oscillation. Why though? Just state the definition of simple harmonic motion. What was the definition? In equation, it looks like this one. But we should give the answer in English in a sentence, which shall goes like this one. Firstly, the magnitude of force on small q should be proportional to the displacement x. And also, its direction is always pointing towards the equilibrium point. And these are the definition and condition for simple harmonic motion to oscillate. In part 2, we are going to calculate the time period of this oscillating charge. It's going to be a pretty long derivation. Let's begin with the given equation. Angular velocity is 2 pi over t. So our target is to make t being the subject, which give 2 pi over omega. The next question is, what is omega? Omega is the angular velocity which is obtained through this equation. A equals to negative omega squared x. Here, instead of making omega being the subject, we should replace x with the Newton's second law, F over m. Then we can make omega being the subject. By making omega being the subject, it will be F over mx square roots. And now we can put these two equations together. T being the subject, which is 2 pi divided by omega. So it is 2 pi times mx over f in the square roots. And all these information they're given in the question. They are m being 0.25 kilogram. X, just leave it as x, because f is going to be in terms of x, 115 times x. By crossing out x, you can get 0.29 seconds. In part C, you're given with a RC circuit, a resistor capacitor circuit. And firstly, we are trying to charge up the capacitor by connecting the switch to point X. So we should focus on the yellow loop. This yellow loop indicates where you can see current flow. Note that I leave the space between the two plates be empty because there is no charge passing through. Only charges will pass through the wires and the resistor as well as the power supply. And the PD of capacitor is being built up. As the charge is being rearranged, there is a stronger and stronger potential difference being built in the capacitor. So the current is reducing from time to time. By studying the V equals IR of the big capacitor, you can see that current is getting weaker, but the resistance is unchanged. The potential difference of big R is reducing as well, starting from 12 volts down to 0 volts. The reason is, in the end, it will stop charging. It will stop its current flow, which means current will be 0, so as the VR will be 0. It will be an exponential drop starting from 12 and an exponential drop towards 0, but not touching 0. Not touching the x-axis. In part 2, with the new information you're given with, we can calculate the capacitance as its discharge. In a discharge loop, we can take a look at this new equation. V equals to V naught E T over RC. It's in your formula sheets. Then we can rearrange to make V over V0, E on the right. The reason is V over V0, it should be 0.5, as only 50% of its initial value is left. And time it took is 5 seconds. Resistance is 20 mega ohm times its unknown capacitance. By rearranging, you can get the capacitance being 3.6 times 10 to the power of negative 7 farad. In question 4A1, it is a definition. So just memorize the following definition and you are guaranteed you can get this 1 mark. Either separating a nucleus or forming a nucleus. Next, we're going to draw a graph. And this graph not necessary to be completely precise, but you still need the general shape to be correct. It will be starting from the left-hand side, going to the peak. The peak is somewhere around 60. Then, after reaching this peak, it will start falling down less rapidly. You can see the gradient on the left is much steeper than the right-hand side. Part 3, we are trying to locate a region at which the stability of the nuclide is the most stable. It is definitely at the peak. The take-home message here is, the greater the binding energy per nucleon of a nuclide, the greater the stability it gets. But why? It all begins with the definitions. The definition could be separating a nucleon from a nucleus. If this separation requires a lot of energy, which means it was very stable at first. However, if there's another nuclide, it just required a small amount of energy, just a very small push, and you can completely separate all the nucleons from it. Probably it is a nuclide made in China. With one small push, the whole building would collapse. In part 4, suggest a solution to solve the problem of having too many neutrons than protons. The decay required is a beta negative particle decay. Note that it must be beta negative particle decay, because in a beta negative particle decay, a neutron is turned into a proton by emitting an electron. At the same time, there is an anti-electron neutrino. Note that this decay equation is not required, but only the first part, only the name, beta negative decay. In part B, there is a decay scenario given. Let's try to draw the equation first. Starting from Pu, going through an alpha decay, and you will reach uranium U. Moreover, we can draw the mass number on it. 238, 4, and this one must be 234. Note that the atomic number, they are not given, which means they are not required. And what do we do with this number? We can study the binding energy on the left-hand side and the binding energy on the right-hand side. After that, we will compare the left-hand side and right-hand side, and that will show the difference should be roughly this number. On the left-hand side, its binding energy per nucleon is 7.568, and there are 238 nucleons. So the total amount of binding energy on the left-hand side should be 1801.184 MeV. On the right-hand side, similarly, we can start with the alpha particle, which is 7.074 times 4, as there are 4 nucleons inside, and it will be 7.600 times 234. 1806.696 MeV. Lastly, we compare the left-hand side and the right-hand side to show the difference. It's a simple subtraction, and you will get 5.512 MeV. In part 2, we are going to calculate the ratio of their kinetic energy, starting with the kinetic energy of alpha divided by the kinetic energy of uranium. And then their kinetic energy should be rewritten as P squared over 2m. P squared over 2m with subscript clearly differentiates their difference. By rearranging, you shall see is P of alpha over P of uranium. This is going as a square. And then is m of uranium over m of alpha. The plutonium, it was stationary at first. Because of conservation of momentum, the plutonium momentum should be the same as sum of momentum of alpha and the momentum of uranium. As it was stationary at first, so it is 0 equals to momentum of alpha and the momentum of uranium. Alpha and uranium, they'll be moving apart with the same magnitude of momentum, but in opposite direction. So it is 1:1 times the ratio of their mass. Their mass ratio is going as their nucleon number ratio, 234:4. The answer is 234:4, or you can simplify as 117:2. In part C, we are trying to use the plutonium to run some instruments of a spacecraft. The amount of plutonium we have is 33 kg. It is the mass. Next one, we have a decay constant of the isotope, and it's lambda. Lastly, we are trying to get the power specifically in kilowatts only. Power, it is the energy delivered per second. And first, we should find what is the number of decay events happening in each second, which means the radioactivity. It is the probability of each given nuclide to decay times the number of nuclide. The decay constant is just the given value, which is 2.50 times 10 to the power of negative 10. How about the number of nuclide? It's not given directly. Instead, you should solve the number of nuclide using the mass. You have 33,000 grams, and for each 1 mole, the mass of it is 238 grams. That you multiply with the Avogadro constant. And this is the number of nuclide available. Put these in your calculator and you will find the radioactivity, which is 2.09 times 10 to the power of 16 becquerel, also known as counts per second. But this is not the final answer yet, because in each decay, the energy being delivered is 6 MeV according to part B. Therefore, the power is the energy released divided by the time taken. The energy released is 6 MeV times now the activity, 2.09 times 10 to the power of 16, happening in each second. So the estimated power delivered should be 1.25 times 10 to the power of 17 MeV per second, and converting this one into kilowatt, it will be 20 kilowatts. Note that if you trace back to the part B1 and if you use 5.51 MeV instead, it will give you here being 18 kilowatt, and both answers are accepted. Part 2, we are going to get the power available after 7.2 years. Firstly, we study the relationship between power and activity. Power is the energy delivered in each decay multiplied with the activity. The activity is a variable, but the energy delivered in each decay is a constant, which means in this case, the power available is proportional to the activity. Note that we have an equation of activity equals to activity naught times e to the power of negative lambda and t. As power is proportional to the activity, we can rewrite the equation in this format. What is the initial power? It is the answer we have in the above, 20 kilowatts. E to the power of negative lambda, which is 2.50 times 10 to the power of negative 10 in second negative 1. And then the time is 7.2 years as well as 2.3 times 10 to the power of 8 seconds. Of course, we are going to take second over the years because we need both expressions in second. These two expressions, they are in second. Lastly, just put everything into your calculator and you will get the answer. It is 18.9 kilowatts. In part D, we are comparing a very special and interesting situation here. Firstly, we have the sun emitting photons towards the spacecraft. And the spacecraft is over here. But between the sun and the spacecraft, there is a filter. And we are comparing, firstly, the spacecraft is stationary and it could be moving away. And no matter is it stationary or moving away, the photon is carrying the same energy reaching the spacecraft, which means the frequency of photon and the energy of photon, they are the same anyway. The energy and the frequency of photons reaching the metallic surface is unchanged. Therefore, the kinetic energy of a photoelectron should be unchanged. And this deduction could be supported by the equation of E max equals to HF minus work function. H unchanged, F unchanged, and even the work function of the metallic surface is unchanged. Therefore, the kinetic energy of the photoelectron is unchanged. Next one, it's about the rate of the photoelectron leaving the metal surface. And we can take this one as an analogy, just like you running towards a bus which is at the bay. If the bus is stationary, you can catch up with the bus very easily. However, if the bus is moving away, then it's much harder for you to catch up with the bus. And this is the scenario of these photons and the spacecraft. The person that is splinting is photon. The bus, it is the spacecraft. Which means the rate at which you can reach the bus or the photon can reach the spacecraft would be lower because of the spacecraft is moving away. So the answer to this one is the rate of emission will be lower as the rate of photon reaching the metallic surface is also lower. In question 5, you are given with a loop passing through a uniform magnetic field. And the loop is moving at a constant speed. It's passing through a magnetic field with a strength of 0.94 Tesla. It's known that it took 3.5 seconds in order to leave the uniform field completely, which means from this end to that end, it took 3.5 seconds. How far are these two red lines apart? It's not 65 centimeters. It's 65 centimeters and 5 centimeters. So the total distance traveled here is 70 centimeters. Then the speed of the object should be the distance traveled divided by the time taken, and it is 70 centimeters divided by 3.5 seconds. It is exactly 20 cm as -1. And you can see that in the question show that it is exactly 20 cm as -1. There is nothing like show that it's something about roughly 20 cm per second. It's exactly 20 cm as -1. In part B, you're going to sketch the variation with the time of the magnetic flux linkage inside the loop. When time equals to 0, the loop was outside of the magnetic field, so the flux linkage should be 0 Weber. And when time equals to 3.5 seconds, it's out of the magnetic field, therefore the magnetic flux linkage is 0 Weber as well. Then we should put two red crosses at these two positions. Next one. It took certain time for the loop to enter the uniform magnetic field. How long did it take? It takes speed equals to distance over time. And then the speed is 20 cm per second. Distance in order to get into the uniform magnetic field, which is 5 centimeters, divided by the time. Therefore, the time is 0.25 seconds. 0.25 seconds. It's going to be starting with a straight line climbing up and then a flat line lasting for a very long duration as the loop is inside uniform magnetic field, and it will be another straight line for dropping down. And then in part 2, you're going to sketch a new graph. It is the induced EMF against time, and it is only the magnitude of induced EMF. Let's take a look at your formula sheets. You should be given with an equation of Faraday's law. The magnitude of induced EMF is the rate of change of magnetic flux linkage. There are three parts, starting from 0 up to 0.25, and there was a constant positive gradient in the magnetic flux against time graph, so that here from 0 up to 0.25 seconds, the induced EMF is a constant value. From 0.25 up to 3.25, The magnetic flux linkage stays at a constant value, which means there is no change. If there is no change in magnetic flux linkage, then the gradient of it will be 0 and the induced EMF will be 0 here. Lastly, from 3.25 up to 3.50, the gradient is a constant value in negative. So the induced EMF should be a constant value, but positive because you are giving the magnitude of it. It's the same magnitude as their gradients are the same. And by connecting all these lines, you get your final answer looks like two vertical buildings on the very left and the very right. Next, in C1, you are going to calculate the maximum induced EMF in the loop when it is going into the field or when it is leaving the field. Note that there are more than one turn inside the loop. There are instead 85 turns in the loop. So, when you calculate using the formula sheet's equation, it's only giving you the induced EMF due to one loop only. So when you are looking at the total maximum induced EMF, you should consider the number of turns as well. It will be n times of the BVL you had in your formula sheet. N is the number of turns is 85. B is the magnetic flux density. It is 0.94. V is the speed of the loop and it's given at 0.20 meter per second. Make sure it is in SI unit. L is the length of the side. It is 5 centimeters, so it's 0.05. Therefore, the maximum induced EMF should be 0.799 volts. And after rounding, it would be 0.80 volts. In part C2, you are going to calculate the resistive force as the coil is moving inside the field as well as when it's leaving the field. The magnetic force is given as N times of the BIL. N, you know, is 85 turns, B is the magnetic flux density, L is the side of the loop, but I is not given directly. And we can still calculate I by using V equals IR. V over R is the current. Meanwhile, V is the induced EMF, so we can get NB epsilon divided by R times L. And the rest is a very simple substitution and calculation. Having this equation and you put them into your calculator, you will get the magnetic force is 1.3 Newton. In D1, we got to show the energy dissipation within the loop from time equals to 0 up to time equals to 3.5. But actually, it's time equal to 0 up to 0.25 and 3.25 up to 3.5 seconds. Because as loop is completely inside the uniform magnetic field, there is no current passing through and there is no energy dissipation. The energy dissipation, also known as the work done, is the product of power times time. The power dissipation inside the loop is V squared over R times time. The V is the induced EMF. It is 0.80 volts. And the resistance is 2.4. Then times the time, it's 0.25 seconds here. And we shall repeat the same for the other part, which means for 3.25 up to 3.5 seconds, the energy dissipation is once again 0.8 seconds squared divided by 2.4 and then 0.25 as well. Then each of these values, they are going to be 0.067 joules for each of them. So when they combine, the total energy dissipation should be 0.13 joules. In part 2, suddenly we have a question about thermal physics. It's about the heating of the wire. As the wire remains in the solid state, so the heat energy flow should be Q equals to mc delta T. How about Q equals to mL? This one is used when there is a phase change between solid, liquid, or gas, but not in this case. Here we have the mass of the wire being 18 gram, and which is 10 to the power of -3 for converting it into kilogram. C is the given value, 385. Delta T is unknown, and the thermal energy flow is 0.13. So the change in temperature is 1.9 times 10 to the power of -2 Kelvin. In question 6 is about the planetary system. Here we have the Sun, the Earth, and a moon of Saturn known as Titan. Their distances are shown in the diagram above. And the intensity because of the solar activity reaching on the Earth is known as the solar constant. It's 1360 watts per meter square. This value is given in the formula sheet. Next, what is the intensity because of the solar activity acting on the Titan? Because of the inverse square law, intensity is inversely proportional to the distance squared. So, now the distance is increased by 9.3 times, which means the intensity should be reduced by 9.3 square times. It will be 1360 divided by 9.3 square. It is 15.7 watts per meter square. According to the question command term, show that it is 16, then we can round it to 16 watts per meter square. In part 2 is about the solar energy reaching the Titan in average. Firstly, the solar intensity reaching the atmosphere of Titan is 16 watts per meter square. However, because of the albedo of this atmosphere layer is 0.22, which means 22% would be scattered, only 78% can pass through. This amount of intensity is equivalent to 12.48 watts per meter square. Those solar radiation passing through the atmosphere will be able to reach the surface of the Titan because the Titan is considered as a black body. It will absorb all radiations. And then this radiation is captured by the cross-sectional area of the Titan and then to be averaged out for the whole surface. What is the cross-sectional area to the total surface area ratio? Is about the cross-sectional area pi r square to total surface area 4 pi r square. So it's a ratio of 1 to 4. Therefore, the intensity being captured and averaged, they are in 1 to 4 ratio as well. Then the required average intensity of the whole surface should be a quarter of 12.48. Then it will be 3.12 watt per meter square. Part 3. After knowing the average intensity of the moon, now we are going to calculate the average surface temperature of the moon. We should begin with the Stefan-Boltzmann law. P equals E sigma A T to the power of 4. And where do you see the intensity? It is intensity being P over A, power over area, equals to E sigma T to the power of 4. E is 1 because it is a black body. So the intensity is 3.12 equals to the sigma times T to the power of 4. Sigma is a number you can get in your formula sheets and put them into your calculator. You will get temperature being 86 Kelvin. Part B, it's about escape speed. So let's get the equation prepared. Square root 2gm over r. And how do we use this equation? We'll use it as a ratio. The escape speed for the Titan and the escape speed for the Earth. It's gonna be their mass ratio, of course in square roots, and the orbital radius ratio, but it is a reciprocal. And their ratio are given in the question directly. So it is square root of their mass ratio, 0.025 to 1, and the reciprocal of their radius ratio, square root of 1 over 0.404. And after simplifying, it is 0.2488. But this is not the final answer yet, because you are trying to get the escape speed for Titan. So Vt is your unknown. It is 0.2488 times the escape speed of the Earth. It is 11.2. So the final answer is 2.79 kilometer per second. Part C1 is a very common derivation. It's about the planetary motion. And all planetary motion, it's between the centripetal force, which is mr omega square, and the gravitational force, g m over r square. To introduce the orbital period, we should replace omega with 2 pi over t, with the square, of course, g big M small m over r square. Next, it's time to make some simplification. Let's say small m and small m, they're crossed out, and it will be 4 pi square r over t square equals to g big M over r square. Lastly, you rearrange to make t squared be the subject, and that is the final answer. 4 pi square r cubed over g big M. Lastly, in part 2, we have an estimation of the mass of Saturn. Of course, we begin with the equation provided in part C1. T squared equals to 4 pi square r cubed divided by g big M. T is 15.9 days, and then you convert it into second for SI units, multiplied by 24 and 60 minutes and 60 seconds. Don't forget the square. Then 4 pi square times r. The orbital radius is given in the question above, is 1.2 times 10 to the power of 9, and then cube. G times m. G is a gravitational constant. You can find it in your formula sheet. It's 6.67 times 10 to the power of negative 11. And then m. Just put these in your calculator and you will see m is equal to 5.4 times 10 to the power of 26 kilogram. Part D1, the molar mass, which means the mass of 1 mole of particle. And in 1 mole of particle, there should be 6.02 times 10 to the power of 23 particle. So in average, each particle, its mass is 4.65 times 10 to the power of negative 23 grams. And turning it into kilogram, it should be 4.65 times 10 to the power of negative 26 kilogram. And it is one more significant figure than the target. In part 2, we are going to calculate the root mean square speed of a particle. And assuming it is an ideal gas, we can start with the average kinetic energy of a gas molecule. It's being 3 over 2 times kT. And it is half mv square. V is the root mean square speed of the particle. So V, after rearranging, it should be 3 kT over m and then square root. K is a Boltzmann constant. You should find it in your formula sheets. T is the temperature of the gas in Kelvin, which is 90 in this case. And the mass is the number given above. Then we can write 3K times 90 divided by the mass in SI unit, 4.7 times 10 to the power of negative 26. Don't forget the square roots. And it will give you 282 meter per second. Part E. Please give a reason whether is it possible to have the nitrogen gas atom leaving the moon Titan. The speed of these gas particles is in Root mean square value 282. And this speed is much lower than the escape speed required in the previous calculation, which is 2,800 meters per second. So it is very unlikely. Question 7, you're given with a conducting sphere. You know its radius, you know its potential, and now you are trying to get the charge of it. And the best way to solve it is to use the equation V equals to KQ over R. V is given 3.4 times 10 to the power of 5. K is the Coulomb's constant. You get it in your formula sheets. Q is the unknown, and R should be converted to its SI unit first. Then you put everything into calculator and you will see Q is 18.2 microcoulomb. Now, this big conducting sphere is connected to a very tiny sphere on the right-hand side. The big sphere, it was positively charged, but the small sphere on the right-hand side, it was neutrally uncharged. So when they are connected, they are considered as one big body only. The one big body should carry one potential and the charges will be rebalanced. There were plenty of electrons on the right-hand side, and now part of them would move to the left-hand side. As the big sphere on the left is positively charged and it's drawing the electrons from the small sphere. The electron flow, they are flowing from the smaller one towards the bigger one. Part B2, we are trying to make a prediction on the charges stored on each sphere. Note that now they are connected together, which means they are considered as one big body only, and they should share the same electric potential. This electric potential is no longer the previous given value, because the old value, it was for the big sphere alone. Now it's the big sphere connected to a small sphere. It will be a new value. And what information do we know about the new values? Firstly, we know that the charges, they can add up to be 18 microcoulomb. Let's label is the charge of the big one and the charge of the small one. Together, they add up to be 18 microcoulomb. This is the first information you know. The second information is their potential are being the same. So potential of the big one and the potential of the small one, they are the same. And we can write QB over R is equals to QS over R. Next, we can cross out the K, and then you can substitute RB and RS with those given information above, which is QB over 48 centimeter equals to QS over 24 centimeter. Having these two equations, you can solve them as a simultaneous equation. And in the end, you should solve QB is 12 microcoulomb. Meanwhile, the small sphere is 6 microcoulomb. The last question, question 8. Part A, give the definition of Doppler effects. Its definition is going as follows. The change in the observed or apparent frequency when there is a relative motion between the source and the observer. Make sure it is the observed or apparent frequency, not simply frequency, not wavelength. Part B, you are given with a simple harmonic oscillations, and you are trying to get the maximum speed of the object with the given frequency and the amplitude. What is the maximum speed of an SHM? You can find it using your formula sheets. There are some hints. First one, you can use this equation as a hint. Also, you can take this equation as a help. Using either equation, you should still give the maximum velocity of an SHM being omega times amplitude. And the omega is 2 pi over t times amplitude, which means it's 2 pi f times amplitude. Luckily, you have the frequency and the amplitude given. Make sure you put them in their SI units, which means you should put 2 pi times 39 times 0.080. Then you will get the maximum speed being 19.6 meter per second. In part C, you are given with a setup just like the radar gun and a car. Because they are both sending a wave towards the target and then looking for the reflected wave. A sound wave going towards the oscillating plate and then the echo coming back from it. And there are two separated Doppler effects. The first one is the emitter one, the second one is the reflected one. For the first Doppler effect, it is a stationary source with a moving observer. So the equation you use should be this one. F prime is the observed frequency, F is the original emitted frequency, so it's 2400 for simply F, V is 340, and UO is the speed of the observer. In this case, it is the maximum speed we had above, just use the given value, 20. And putting these into your calculator, you will get 2541 Hz. For the reflected wave, it is another Doppler effect. Let's take it as the double prime because it is the second Doppler effect. It's followed by the first Doppler effect, and it is a moving source in this case. So we have V over V minus US, stand for an approaching source. The F double prime is the unknown here, and F prime is the previous answer, 2541. The wave speed is once again 340. The speed of the source is 20. And putting these into your calculator, you will get your final answer as 2700 Hz. In part D, you are given with a diffraction grating, with its number of slits to be increased, but the slit separation and the slit width, they are staying the same. Let's focus on the number of slits first. The number of slits is increased, therefore the width of the primary maxima is getting narrower. Also, the intensity of the secondary maxima will be decreased. How about the effect of the separation and the width? As the separation and the width, they are staying the same, according to the equation, d sine theta equals to n lambda. As the d is unchanged, so as the rest, even the angle theta is unchanged. Therefore, we have the angular position being unchanged. This is the end of the complete solution. Feel free to leave comments at the bottom, and I will see you next time.